So we're continuing today by looking at chemical equations, and we're going to start by going through some balancing techniques. We're going to do a couple of examples of how to balance equations. So for those of you that haven't done the skill builder yet and you haven't had as much time to practice this, I'm going to show you some of the things that I do, some of the tips and tricks I have that make balancing equations a little bit easier. For those of you that went through the skill builder, you've seen some of this already. This will be kind of a good review. But once we get through kind of this balancing piece, then I'll get into talking to you about how we use balanced equations to drive calculations. So we're starting with this practice problem. We have the reaction of nitrogen dioxide and water to make nitric acid and nitrogen monoxide. Now, the first step is if I'm just given words like that, I need to turn it into a chemical equation. So I need to use my nomenclature knowledge to turn those words into chemical formulas. And again, if you went through the skill builder, you've seen some of that already because we did word equations in part 2 of that skill build. If you're not there yet, it's coming. Now, in terms of atom economy, the idea that we are going to monitor our equation and the number of atoms on each side so that we can do good stewardship in terms of knowing that every atom that was on the reactant side is on the product side. I'm going to list out all of the elements in this reaction. So there's nitrogen, there's oxygen, and there's hydrogen. Now on the opposite side, I'm going to do that same thing. Now, order here doesn't matter. I usually list out the reactants in order of appearance just because it's kind of easy to track that way. What you want to make sure is that whatever you do on the reactant side, make sure that it's even on the product side so that you can just look straight across and determine if the values are the same or not. So looking at the equation as it sits, I have 1 nitrogen and 3 oxygens, the 2 from here plus this one here, total of 3, and I have 2 hydrogens. And on the product side, I have 2 nitrogens and 4 oxygens and 1 hydrogen. Now, if we go backwards to the slide where I introduced, some tips and tricks that I have, one of the things that will come up is when we're balancing equations like this, we usually want to start from simple to complex. And what I mean by that is oxygen is probably going to be the last thing that we look at. And the reason it's going to be the last thing that we look at, oxygen is in all 4 of these compounds. So when I start throwing coefficients in here, it's going to be really difficult for me to try to figure out how to balance the oxygen, because every time I change something, oxygen's going to change along the way. So as a result, we're going to leave oxygen for last. In addition to leaving oxygen for last, we're also looking at this and saying, okay, well, hold on, nitrogen is in 3 of the 4 compounds. That's not as complicated as oxygen, but it's still kind of complicated. The simplest one is the hydrogen. Hydrogen is only on 1 compound in the reactant, 1 compound in the product. It is out of balance. So that is where we would start this particular discussion in terms of how to balance that. So as I'm walking through here, we can see initially speaking that every one of our elements is out of balance. But like I said, if we start simply, we're going to look at hydrogen first. And so to balance out the hydrogen, I'm going to need 2 of the nitric acid molecules. And in getting 2 of those nitric acid molecules, I'm going to double the hydrogen, double the nitrogen, and double the oxygen in that compound. And so not only does it change my hydrogen number, it changes all 3 numbers actually in this particular case. Now that seems like it would complicate things, but it actually tells us what the next step is going to be. Because while I got my hydrogen balanced, I can look at this and say, okay, nitrogen is definitely not balanced. Oxygen is definitely not balanced. But the nitrogen that I need only exists in one compound on the reactant side. So if I triple that reactant and make 3 nitrogen dioxides, it just so happens that in addition to balancing out the nitrogen, it also is going to balance out the oxygen. And what's great about this is usually how it happens. When we go from simple to more complex, as we're balancing out the simpler elements, it usually hits a point when we're balancing the complex ones that it'll either work itself out without us really doing anything. We never actually tried to balance the oxygens on their own. They just got balanced out when we balanced out everything else. And if it doesn't work out exactly like this, it'll work out to the point where it'll be pretty easy to see what the last step is. So going back here, it was easy to see that to get the nitrogen balance, I had to triple the nitrogen dioxide. That was the only way to get it out. That is another kind of thing that we can tend to see happening, where we get to that last element, that thing that is incomplete, and we look and say, oh, it's the only one left. And it just so happens that the thing that needs to balance it out is on the other side all by itself. I can balance it there. And so by doing this atom economy kind of method here, we always can be certain that we have a balanced chemical equation, because we can see, okay, every nitrogen's accounted for, every oxygen's accounted for, every hydrogen's accounted for. Now, when we get to redox reactions, where we're talking about the movement of electrons in addition to the movement of atoms, we'll need to concern ourselves with the idea of charge balance as well, but that's not a discussion for right now. Let's take a look at some other examples. So here I have the example of, I've got octane, C8H18, reacting with oxygen to make carbon dioxide and water. Right away, I should recognize this as a combustion reaction. I've got a hydrocarbon reacting with oxygen. The products are carbon dioxide and water. From an accounting standpoint, I've got carbon, hydrogen, and oxygen. So I'm going to put each of those on both sides. I've got 8 carbon, 18 hydrogen, and 2 oxygen as my reactants. I've got 1 carbon, 2 hydrogen, and a total of 3 oxygen, 2 from the carbon dioxide and 1 from the water. So sometimes I find that kind of looking at each compound individually helps me to make sure I'm keeping track of the total number. And so you'll see me do this sometimes where I'll put a little math problem on the bottom there, just so I know where that 3 came from. So One of the other tricks that I can show you that helps with balancing equations is looking for kind of markers like these. Anytime I have a compound that has multiple subscripts on it, I can use that compound to drive my chemical balancing here. And what I mean by that is this carbon is found only here. This hydrogen is found only here. So using those subscripts, I can write out the coefficients for carbon dioxide and water and be pretty certain that they're going to lead me in the right direction. So in order to get 8 carbon, I'm going to need 8 carbon dioxide. In order to get 18 hydrogen, I'm going to need 9 waters because there are 2 hydrogens in every water. 9 times 2 gives me the 18. So when I do the process here, I'm going to have to reconfigure my numbers. My carbon becomes 8. My hydrogen becomes 18. And I now have 16 oxygen plus 9 more for a total of 25 oxygens. Carbon's balanced, hydrogen's balanced. Now we get to oxygen. Now, if we were doing it without this subscript trick, we would basically arrive at the same place. Oxygen is in 3 of the 4 compounds. We would save oxygen for last anyway. And now that we can see that the relationship here is actually pretty close to simple. I only have oxygen in the one location. I just need to get 25 of them. Problem is, they only come in pairs. So I can't get 25. So I've got to do something about that. And there are 2 approaches that we can take. One of them is we can say, who cares about I can't make an odd from evens? Why don't I just use a fraction? So the fraction 25 over 2, 25 halves or 12 and a half multiplied by 2 would give me 25. I've got myself a balanced chemical equation. We run into some problems with this approach, though. If we're talking about molecular kinds of reactions, what does half of an oxygen atom or what does half of an oxygen molecule look like? If oxygen exists as these O2 molecules that are linked together with chemical bonds, I can't just simply break them in half to get the proper number of atoms. It doesn't work like that. So if we're looking at this chemical equation from a molecular standpoint, fractional coefficients don't make a whole lot of sense. And for that reason, when you start looking at like homework problems, textbook problems, you're not going to find fractional values here. You're going to find whole number values. And so if that's the case, then what we need to do is we need to turn the fractional values into whole number values, which means we need to multiply by 2 to get rid of the half. And our final equation would look like this. 2-octane plus 25 oxygen makes 16 carbon dioxide and 18 waters. And so from that standpoint, this takes care of the molecular problem that we might run into. Now, that being said, most of the time, we're not concerned with the molecular basis of chemical reactions. If we're doing a reaction in lab, we're not dealing with one molecule of octane and trying to create exactly 8 molecules of carbon dioxide and 9 of water. We're usually measuring things out. We're talking about things on the mole scale. And on the mole scale, does half of a mole make sense? Does half of a mole work? Yeah, because you know what half of a mole is? It's 3.011 times 10 to the 23rd molecules. That's a real number. That's a whole number. I don't have to worry about that. So in the macro scale, we can use chemical equations that have fractions in them, because we understand that does a half of a mole or a quarter of a mole is still a whole number of molecules. But just as a word of warning, textbook active, they're going to be looking for whole number ratios. Madeline, you have a question? So chances are, if we're talking about compound plus oxygen making two new compounds, we might still be talking about combustion. It depends on what those two compounds are. So combustion is not limited just to hydrocarbons. It basically talks about the burning of anything in oxygen to create oxide compounds. So if I had hydrogen sulfide gas, for example, H2S, and I burned it, and it made water and sulfur dioxide, that would still be considered a combustion reaction, because what we're getting is the oxygenation of the hydrogen from hydrogen sulfide and the sulfur from sulfur dioxide to make oxide products. That would still be considered combustion. It's just not the normal kind of combustion, because usually when we talk about combustion, we talk about hydrocarbons. But yes, it does extend beyond those. All right. Questions with this example? Combustion reactions tend to be the biggest culprits for these kinds of fractions. But once you know what to do with them, it's actually not too bad to work with at all. All right, let's look at another example problem. We're going to balance this equation. We've got an oxide of iron reacting with hydrogen to make iron metal and water. This would be an example of a single replacement reaction. Why single replacement? Well, we can see hydrogen here acting as a metal, acting as a positive ion and kicking out the iron. So that's why it is single replacement. As far as balancing goes, I've got iron, oxygen, and hydrogen in my compound. Starting off my inventory, 3 iron, 4 oxygen, 2 hydrogen. On the reactant side, 1 iron, 1 oxygen, 2 hydrogen on the product side. In this particular instance, we don't really have a most complicated element. So we can't use that as our starter, but we can use the subscripts here as starters. The 3 subscript on the iron oxide can be used to make a coefficient on the iron. The 4 subscript on the iron oxide can be used as the coefficient for water. That's going to square up the iron and square up the oxygen, but it is going to throw the hydrogen out of whack. But luckily, hydrogen is by itself on the reactant side of the equation. So I just need to put a coefficient of 4 there to get it to balance out again. So this subscript trick is really useful in a lot of applications when we're trying to balance things out, especially when we don't really have a good starting place otherwise. Now, if we happen not to have subscripts at the ready, then we've got to fall back on our other ideas. Clustering ions together if they exist, going from simplest to most complicated when we're trying to figure out the order to balance everything. All right, I'm gonna let you try one here now. So we've got the equation, dinitrogen pentoxide decomposing into nitrogen and oxygen. Think of your answer here like a code. I want a 3-digit number. 3-digit number telling me the 3 coefficients that go along with this equation in order. So if you come up with fractions here, you're going to have to convert the fractions into whole numbers to get the code right. Three-digit number. So first digit is the coefficient on the N2O5. Second digit is the coefficient on the nitrogen. Third digit is the coefficient on the oxygen. No spaces, no commas. So no, just the 3 numbers. Now, the beauty of this equation, the beauty of balancing equations in general, is that there's no one way to do it. There are lots of ways that you could have gone about this. You could have done the subscript thing. You do the subscript thing, you go 2 and 5 here. That had given you 4 and 10, and you would have recognized you had to double this to get the code 225. That would have been one way to go. Another way to go would have been very similar to what we did with the combustion equation, where you look at this and go, okay, how do I get 5 out of 2s? Well, I turn this into a fraction. 5 halves turns this into a 5. Now it's balanced. But since I can't have fractional numbers, I got to multiply everything by 2. And so I would get 2 N2O5 coming into 2 nitrogen and 5 oxygen. Still get the same thing, 225, get it a slightly different way that time. So there is no one truly correct way to balance equations. There are lots of different ways that you can go. However, you want to try to save yourself some time and aggravation at the very least by just following some of those guidelines that I set forth. And so the subscript trick, the clustering trick, those are all things that are useful to you and can help you do it faster. And so what should happen over time is that as you get used to this, the need to do this accounting is going to be less and less, where you can just start to look at the equation and recognize, oh, okay, I see what's going on here. And you can just start putting coefficients in. That's called balancing by inspection. And that's something that it just is a skill you acquire as you do this more often. So if you're there now, yeah, I'm not requiring you to do this anywhere. But if you're unsure, this is a way to make sure that you are accounting for everything appropriately. All right. Any questions about balancing equations before we move on to stoichiometry? All right. So the main meat of this module is stoichiometry. Stoichiometry is based out of the law of conservation of mass. So with balanced chemical equations, we focused on the law of conservation of matter, the idea that matter, atoms, couldn't be created or destroyed. Well, that's a great idea, but we don't usually measure atoms. We usually measure masses. And so for masses, we need to use the similar kind of idea. Mass cannot be created or destroyed. What stoichiometry allows us to do is it allows us to do calculations to help to establish that relationship between our reactants and each other and their masses, and the products and each other and their masses. How stoichiometry is different than what we did in module 2 is really only in one area: balanced chemical equations. In module 2, we were only concerned with conversions to moles. I take grams and I convert them into moles. I take particles and I convert them into moles. I take moles and I convert them either into grams or particles. All that we are doing is extending that by allowing us to look at how does one substance relate to another substance in a chemical reaction. And that's where the balanced chemical equation comes in. Now, stoichiometry itself kind of has a funny name, and because it's chemistry, and we naturally think of chemistry as being complicated and hard, and we throw on top of it a really long word that doesn't seem to make a whole lot of sense, like stoichiometry, we naturally think that stoichiometry is something that can only exist in a laboratory situation with really complicated calculations. And the reality is, stoichiometry is something that we use regularly. How many of you have ever worked in a fast food restaurant at any point in time in your life? Okay, I worked at Wendy's for 2 years when I was in college. And I did pretty much every job while I was in there. My least favorite job was the sandwich maker, though. Because in the sandwich maker station, you got this tray in front of you that has all the ingredients, and you have to put them on in the correct order, and you have to put on the right amounts of everything, or else you get someone right here yelling at you about how you made the sandwich wrong and need to try again. Well, that construction, let's say I'm making junior bacon cheeseburgers, it has a very specific recipe if you follow it to the letter. You have to have a bun, you have to have the meat, you have to have the cheese, the bacon, the lettuce, tomato, and the mayo. And they have to put it on in a certain way, in a certain order, or else it's not right. Well, that's stoichiometry. Now, it's on a different scale. At no point in time did I have to take the burger patty and weigh it out on the scale to figure out how big it was. But at the same time, that burger patty had a certain amount of mass to it. I had to use that particular type and not another type of patty. There were pieces to that were unique, scale. We can think about the same kind of thing when it comes to s'mores. Now, when we start getting into food items, recipes come into play. It's not exactly a perfect analogy, but let's just say that there is a universal recipe for s'mores that is dictated by your textbook, and it involves these 3 ingredients in these particular amounts. I have to have 2 graham crackers. I have to have 1 marshmallow. I have to have 3 squares of chocolate. Deviate from this in any kind of way, it's not a s'more anymore. It's something else. Well, those dictates can tell us how many s'mores we can make with a certain amount of ingredients. And that is stoichiometry. The only difference between this example that we kind of do on a daily basis when we make a recipe versus what happens in a chemistry lab is just what our point of reference is. In the recipe world, we reference things to cups, or in this case, squares, specific items. In the chemical world, we reference everything to moles. And so, as far as calculations are concerned, there are really only 3 calculations that we need to know how to do. We need to know how to turn things into moles. So whether that is using Avogadro's number to turn particles into moles, or moles into particles, or mass, using molar mass to turn grams into moles, or moles into grams. The other thing we need to know is the mole ratio. The mole ratio comes from the balanced chemical equation itself. And so we've covered this kind of calculation already. This is the thing that is different. That is the thing that we're going to have to kind of wrap our heads around here in Module 4 to extend our knowledge from Module 2. Now, luckily, we can help ourselves a little bit. This is a diagram I have used for, well, 2011 it says there, so let's go with that. The idea here, this is an organizational system. Tells us what kinds of calculations we need to do to connect one piece of information about a substance to another piece of information about another substance. Now, we had a slight version of this in Module 2. It looked like that, where all we were doing was connecting moles of substances to grams of that substance or to particles of that substance. Like I said, the only thing that we are doing differently here is we're connecting one substance to another using the balanced chemical equation. And so what we want to think about as we are kind of connecting these all together is that these blue arrows represent calculations that we have to do. So if I need to go from here to here, grams of one substance to moles of another, I can follow this map and recognize that there are 2 calculations that I'm going to need to do. 1 molar mass calculation to turn the grams of that substance into moles, and then using the balanced chemical equation to turn the moles of that one substance into moles of another. So think of this as a way of organizing yourself if you're not sure what to do. And so my suggestion to you, find yourself a computer lab and just pull up this slide directly and print this individual slide so that you have it. And so that way you're not digging through your phone, you're not digging through other materials to find it when you're working on your homework. It's right there and you can say, oh, I'm starting here, I'm ending here, this is how I link them together. Like a lot of things that we've been doing, this is a process, it's a procedure. As we practice it, we get better with it, we don't need this as much. But as we kind of get started here, it's going to be a good thing for us to have to kind of organize ourselves. So let's take a look at an example problem. Here we have cuprite, Cu2O, copper 1 oxide. We can convert cuprite into copper by reacting it with charcoal, carbon. The balanced chemical equation is given to us. What we want to know is how much cuprite and how much carbon are needed to make a 256-gram copper bracelet. Now, from an organizational standpoint, we're going to come back to our map here and recognize we're starting with grams of copper. Now, in the end, we're trying to turn it into grams of carbon and grams of the cuprite. The process to get there is going to be basically the same for both. I need to take those grams of copper, turn them into moles, turn those moles of copper into moles of whatever the product is that I'm interested in, and then turn those moles down into grams using the molar mass. There are 3 blue portions to this, so each step, each conversion is going to require 3 calculation steps. Now it's just a matter of putting those steps actually together. So we start with our 256 grams of copper. Our first step, if we went back, would be to turn the grams of copper into moles. For that, we need the molar mass of copper. Molar mass of copper, 1 mole of copper is 63.55 grams. Got that straight from the periodic table. My grams of copper cancel. Here's my second step. This is the step that we haven't seen yet. We want to turn moles of copper into moles of cuprite. How do I use the balanced chemical equation to do that? This is where the coefficients come in. The coefficients tell us that every 2 moles of cuprite will react with 1 mole of copper or carbon to make 4 moles of copper and 1 mole of carbon dioxide. So I literally just drag down the coefficients for my balanced chemical equation to fill out this portion of the conversion. Moles of copper cancel. I'm left with moles of cuprite. Last step, I need to turn the moles of cuprite into grams. All right. Common mistake made here is trying to put the coefficient in this step. We don't need the coefficient in this step. We're just doing a molar mass conversion. Molar mass conversions are 1 mole. So I've got 63.55 for copper times 2 because there are 2 of them, plus 16 for oxygen because there's 1 oxygen, 143.10 grams is the result. My moles of cuprite cancel. 256 times 2 times 143.1 divided by 63.55 divided by 4 to 3 significant figures because I only had 3 here at the start is 288 grams of cuprite. Now for the second conversion, we are going from copper to carbon. it's going to start out the exact same way. 256 grams of copper. We need to turn the grams of copper into moles. Luckily, we already know that conversion because we've already done it once. 63.55 grams in every mole. My second step, I need to turn the moles of copper into moles of carbon. Again, I use the balanced chemical equation. Since carbon does not have a coefficient, it must be 1. So I've got 1 carbon and 4 copper. My moles of copper cancel. Last step, 1 mole of carbon weighs 12.01 grams. So my moles of carbon cancel. I'm left with just the carbon grams. 256 times 12.01, divide by 63.55, divide by 4. To 3 significant figures again, 12.1 grams of carbon. So when we talk about stoichiometry, it's very easy to get brought up into thinking that this is a lot more complicated than it actually is. You've done this calculation. You just haven't done it this way. The only thing that you didn't know was this conversion here in the middle that linked together the two substances. And the closest thing that you had was in module 2, there were a couple of times where we asked you how many atoms of carbon are in this sample of carbon dioxide, where you had to take the carbon dioxide, turn it into carbon, and then turn it into particles. That's the closest thing that we had, where we had to use the chemical formula to link together the molecule to the atom. This is kind of similar. We're using the balanced chemical equation to link two substances together. When we come back to this on Monday, we're going to talk about a concept known as limiting reactants. And with limiting reactants, we're going to talk about what happens when we don't have enough substance to make everything react. In the meantime, don't worry too much about 4-2 until after the exam on Friday. Spend your time this next couple of nights getting ready for the exam. On your way out, hit the stoplight question, and I will see you on Friday. Have a great afternoon.